right? I sent an email I put on Moodle? Yeah. Okay, good. So I said the momentum in the system, total momentum, does not change. Closed system, unaffected by external stuff, forces, whatever. So if we have a collision of two objects, we have object 1 with mass 1, and it's going at a velocity we call u1. It's a vector, this is how fast it's going. And then we have some other object with mass 2, it's going at a vector of velocity u2. So you have these two things, they're like along, imagine two, let's say, pool balls, billiard balls, or whatever. If you've already done the lab, this will make sense. If you haven't done today's lab, it will make sense when you get there. We're doing that. So that's going to equal mass 1 times v1, v, this being, so ui, velocity before collision, vi, velocity after collision. Okay, so it's going to equal m1 v1 plus m2 v2. So this, I said mass times velocity was momentum. Okay, we had multiple things, we just add them up. So total system momentum before the collision, u1 and u2, equals total system momentum after the collision, v1 and v2. Okay? Now, for a given M1, M2, U1, U2, there are infinite sets of V1 and V2 that will satisfy this. Okay? There's a lot of infinite ways of satisfying this. We would need much more information. And right now we have one equation with essentially 4 unknowns. Because say we know all the stuff in this, 100% given. We know everything over here, right? We know M1, we know M2, but V1, we don't know its direction and we don't know its magnitude. V2, we don't know its direction and we don't know its magnitude. So we got one equation with this hill, 4 unknowns, at least. Depending on how you think about its direction. If we say this is in 3 spaces, its direction, I would say, is not 1 unknown. It's like possibly 3 unknowns. So we got lots of stuff going on. Even if we were to limit this to, and we're already start talking about a 1-dimensional system, which means things are just moving along the line. And not just 2-dimension would be, things moving around in a plane like that. 1 dimension, things are only going, just going along. We're going to talk about the special case of a 1-dimensional system. But even in a 1-dimensional system, we still have 2 unknowns. Even if we know V1 and V2, they're either going that way or that way, we don't know their magnitude. So we can have 1 equation, 2 unknowns, so we can't solve this. So we need more information if we're going to. So now I'm going to talk about kinetic energy very briefly, because that's how we're going to get our second equation to be able to solve this, is by using kinetic energy. So kinetic energy, it is a scalar quantity. So before I said momentum was a vector quantity, meaning it has direction, not kinetic energy. Kinetic energy does not have direction. There's no direction to it. It's just a number. The units, but it's just a number. Translational, I'm going to be abbreviating kinetic energy KE a whole bunch of times. So translational kinetic energy is 1/2 that's a vector. V with no hat, that's the magnitude of the one with the hat, all right? So that's translational. Does everybody know what I mean by translational? Translational means it's moving about in essentially 3 dimensions, but it's just moving around. All right? It is not spinning. So rotational kinetic energy is 1/2 I omega squared, where I is the moment of inertia about the axis of rotation. Oftentimes we'll do I about the center of gravity of whatever object it is. It doesn't have to be. Okay? So it's about the axis of rotation. What axis of rotation, you might ask? Whatever axis of rotation our omega is going around. Okay? I mean, because I could take, imagine that I myself am a totally massless object. We have this guy right here. It is rotating like that. Where's the axis of rotation? Somewhere around here. So we would have to calculate I about this axis of rotation for this object located out here. Now we could also just sort of spin it right about its center of gravity, and that would be a different I, much smaller, right? So you have to calculate the moment of inertia about its axis of rotation. I'm not going to be giving you problems to calculate the moment of inertia coefficient. We're going too far into other classes. If you need the moment of inertia, I can give it to you. Okay? But you would need to know what to do with it. And so, an omega here, there. So omega has to be in radians per second. You do this like in degrees per second or something, it ain't gonna work. Alright? To make this equation work, this guy needs to be in radians per second. Alright. Now I'm gonna erase this side over here. Okay?
Can I take down that bottom equation?
Yes.
Thank you.
Gonna erase this stuff over here then?
Well, no, go ahead and start erasing this side, but start at the top. Okay, I'll do it tomorrow. Thank you.
Cassie's gonna let you copy? I'm fine with that. Okay. So, with collisions, we have elastic collisions, we have inelastic, we have perfectly elastic collisions, which we will generally be talking about because it makes life so much easier. You have, it's a perfectly elastic collision, so in elastic collisions, total kinetic energy, E, of the two bodies, and if there were more than two, it would still hold true, is the same before and after the collision. Okay, no kinetic energy is lost. You have the same kind of two things come together, they whack, they bounce off or whatever. You have the same kinetic energy before and after. In the real world, that's rarely true. Oftentimes, some of the kinetic, almost, pretty much always, I don't know. I mean, you do have like atoms bouncing around, hitting each other inside the material at an atomic level. You get pretty close to an actual elastic collision. But shy that, pretty much everything isn't actually elastic. But it makes our math so much easier that we tend to do a lot of elastic collisions. In the real world, they're at least partially inelastic, which means that some of the kinetic energy is turned into something else. Heat, vibration, well, vibration is still kind of kinetic energy, but heat, sound, other stuff. Okay? But in an elastic collision, total kinetic energy, same before and after, none of it's lost. Okay? And so, for our this was momentum right here. So I'm going to write a similar equation this time for kinetic energy. So I have my M1 U1 squared over 2. That's my formula for kinetic energy, 1/2 mv squared. Notice I don't have my little hat anymore. Now I'm just talking about the magnitude of the velocity. So I have that plus m2 u2 squared over 2. So that's the kinetic energy before the collision, or these were the velocities of the guys, these two things before the collision, equals m1 v1 squared over 2 plus m2 v2 squared over 2. So the kinetic energy is the same before and after in an elastic collision. All right? And notice this is all translational. You could theoretically have, and very easily could have a collision that would start one of them spinning. And so you'd have some rotational kinetic energy. If maybe when they're coming in, they're not, then they hit and the one starts spinning. It's translating, but it's also spinning. That would still be an elastic collision. I'm not going to do that to you though. Okay? We'll do stuff that will just be translation. Probably. Unless I think it's fun to do that something else. I'll warn you that we're using it. All right. So now we have, in our one-dimensional system, okay? In our one-dimensional system, we now have two equations, this one and this one, with two unknowns, v1 and v2. We're assuming all this stuff's given. We know u1, we know u2, we know m1, we know m2, all that's given. Now we have two unknowns, v1 and v2. It's just for the one-dimensional system. All right? So